And we've got more practice with all of our derivative rules and techniques. A linear approximation will be an overestimate in a concave down interval if you think you've forgotten. Simply make a diagram and you'll see that, yes, the tangent line is higher than the curve itself. So that would be true. The derivative of 7 to the x. Well, think of our rule for a to the x. Our derivative of a to the x is a to the x ln of a. So this should be 7 to the x ln of 7. So not the power rule or some version of it. So this is definitely not the derivative. The derivative of 7 to the pi, that's the trick question we keep seeing over and over again. That is a constant, so the derivative would be 0, so this is false. The derivative of inverse cosine, nope, this is the derivative of inverse tangent. So it is familiar to us, but it is not the correct one. The derivative of inverse cosine of x is negative 1 over the square root of 1 minus x squared. So that one is also false. In number 5, we need to do implicit differentiation, and then we want to find a specific slope of a tangent at the point 3 comma 1. So implicit differentiation here, I don't have much space for work there. So we need to do a product rule on this, call this u and v. So x times the derivative of y cubed, and that requires a chain rule on the y, plus, so there's our uv prime, plus our vu prime, so we need the y cubed times the derivative of x is just 1, so that's only the derivative of our first term. And then, my goodness, we've got another product rule right behind it. So now the derivative of xy. So there was our first product rule. Maybe let me switch here. For the derivative of xy would be the first times the derivative of the second would just be 1 with a chain rule, dy dx, plus the v, that's the y term, times the derivative of u, the derivative of x is just 1, and then we have this equals 6 to go yet, so this would be equal to 0. So what do we have here? So I have this term that has a dy dx, and I have this term that has a dy dx. So as I rewrite these to clean this up a little bit, 3xy to the second dy dx, and then I'm going to put this term next, the x plus x dy dx, and I'm going to move the other two terms to the other side, so it looks like what, a negative y cubed and a negative y. So when we factor our dy dx, can we divide right away? So we would have this value over 3xy squared plus x. You might have factored a negative 1 out of that numerator. And now we want to find that derivative such that x is 3 and y is 1. So we want to put 1 in for y. So the opposite of 1 cubed would be negative 1 minus our y. And in our denominator, we want 3 times x. 3 times x is 3. Times y squared would be a 1 plus our x value. So it looks like our denominator is our numerator is a negative 2, and our denominator is a 12. So hopefully we have a negative 1/6 up here as a choice. So we're going to take letter D in our multiple choice question. All right, derivative of arc sine. So we want to find f prime first, and then we want the numeric derivative specifically at 8. So f prime, the derivative of arc sine, is 1 over the square root of 1 minus our glob squared, 16x squared, times the chain rule on the glob. So let's think about this glob. Could we think of that as 4x to the negative 1? So our chain rule then would be a negative 4x to the negative 2. All right, so normally we would say that you should remove the complexity. How you would do that, by the way, would be to change this 1 into an x squared over an x squared, and you would bring a 1 over absolute value of x out of that square root. But here we're lucky that we're doing a numeric derivative, so we don't necessarily have to clean up the algebra. We can clean up the arithmetic. So instead of doing all of that work, we could just take this value that we have and put 8 in there, and let's see what happens. So here, I guess I just don't have enough room here. Let me go over here, f prime of 8. So we would have 1 minus, so think what happens when x is 8 here. We would have 16 over 64. So we would have a 1/4. And put an 8 here, that's in the denominator. So we would have a negative 4 over a 64. So that would be a negative 1/16. Okay, so now we've got to see what happens here. So now we're back to that same situation that we've had in previous problems. So this 1 right here, we got a common denominator. We thought of this 1 as a 4 over 4 so that we could simplify. So how can I rewrite this here? This negative sign I'm going to put over here. The 16 I'm going to put there. And then I'm going to factor a 1/4 out of that square root. And it looks like, oh, I guess I don't actually have to do that. Well, yeah, that's good. And then I would have a 4 minus 1 left. That works. Okay, so the square root of 1/4 is 1/2. So those two are going to leave us with an 8. So I don't know if I have much faith in my work here. I might need to double check this. And I think I don't see any errors there. So let's find out. Choice A. All right. The derivative of a log, so f prime of x, is 1 over x, natural log of the base. And now we want to do a numeric derivative, specifically when x is equal to 1. So it looks like we would just have 1 over natural log of 2. So that one at least helps speed up our process. Here we have x in the base and x in the exponent. So this is where we must go to logarithmic differentiation. Take the natural log of both sides in order to bring that exponent down in front. So now we have to do implicit differentiation. So this is the case where you must do the log when you have variable in the base, variable in the exponent. All right, implicit differentiation with respect to x. So the derivative of natural log is 1 over the glob times the chain rule on the glob. On the right-hand side, we've got a product rule. This is our u function and our v function. You could put the 2 on the outside of the product rule if you wish. So we'd have our u times the derivative of v. The derivative of natural log of x is 1 over x. No chain rule needed on an x, plus v, the natural log of x, times the derivative of u, that's a 1. All right, do these all start looking familiar? We've done problems like these repeatedly. So those two x's can cancel. So we've now got a 2 times a parenthesis 1 plus x, and now we want to move this y to the other side. So our formula for dy dx at this point, when I bring y to the other side, I'm going to write it in terms of x. So go back to your original. So instead of putting y here on the other side, I'm putting what y is equal to. Look at your original problem. And then we have, there's our y. and then we've got a 2, and then we've got a 1 plus ln of x. So we could clean that up a little bit better, but look at what we want to do. We want to find the derivative. dy dx is the same as f prime. We want to find that when x is equal to 1. So we want 1 to the second power times 2 times 1 plus ln of 1. We know that the exponent on e that produces 1 is 0. So we've got a 1 times a 2 times a 1. So I am coming up with a 2. So that would be our choice A. All right, again, we've seen this before, so I'm not sure if I meant to give you the same practice repeatedly, if that was a mistake, or if I wanted you to just get additional practice. But I think I've just done this one in a previous video. Let's do it again. Let's do it again. All right, so change it to this form. And then we know the only way when we have a variable in the base and a variable in the exponent is to take the natural log of both sides. So then what we're doing here is taking the power and bringing it down in front. That's why we need to do logarithmic differentiation. All right, now implicit differentiation with respect to x. So 1 over y, chain rule on the y, equals, and then here was our product rule. Remember, we did the x as the u function, and this natural log as v. So we've got u times, and then we got to do our v prime. The derivative of natural log is 1 over the glob, times then the chain rule on the glob. And then we would do another chain rule. If this weren't a single x, we'd still have another chain rule. So there's our u v prime plus our v term times the derivative of u prime, that's just 1. All right, and we want to find this. We can clean it up some more, or we can just plug in the arithmetic at this point. And remember, that's how I recognize this at pi over 2. Remember that cosine is 0 and sine is 1. Okay, so we really should move this y to the other side, though, I guess, first. So dy dx. And when we multiply the other side by y, we're going to put what it's equivalent to. Y is equal to, when I move this y to the other side, y is sine of x all raised to the x. So that's taking the place of multiplying by y. All right, and then we had x cosine of x over sine of x plus natural log of sine of x. Okay, so now we want to do this f prime, dy dx is f prime at pi over 2. So the sine of pi over 2 is 1. So we'll have 1 to the pi over 2. Remember, any power of 1 is still 1. X is pi over 2. Cosine of pi over 2 is 0. In the denominator, sine of pi over 2 is 1. Sine of pi over 2 is 1, and the natural log of 1 is 0. So when we came up with all of this, we got 1 times 0 plus 0. So that was, I remember commenting all that work just to get a 0. And now we did it again. Okay, number 10, one more logarithmic differentiation, because we have x in the base and we have x in the exponent. So we write it in terms of y, and we could rewrite this square root of x as x to the 1/2. So I think I like that as our exponent, 1/2 of x. And then we take the natural log of both sides. Haven't done any derivatives yet. Just take the natural log of both sides and bring that exponent down in front. All right, so now we're ready to do the implicit differentiation. So the derivative of natural log is 1 over the y times the chain rule on the y. And if we want to keep the 1/2 out of the product rule, we're going to use x as our u function and natural log of x as our v function. So we've got to do a product rule. So our x times the derivative of natural log of x, so there's our uv prime, plus our v term times u prime, the derivative of x is 1. All right, so those x's cancel. And we need to move this y to the other side. So dy dx, or if you prefer, f prime of x. And our y term, when I move the y, when I multiply y on the other side, I can put it back the way it was originally. So when I multiply this y term, I'm going to put it right here with this coefficient. So 1/2 of square root of x to the x, or x to the 1/2 x power, your choice. That's our y term right there. And then our brackets here were a 1 plus an ln of x. Okay, so now we've got one thing left to do in that problem. Find f prime of 1. So at least we get to substitute in a 1 here. Makes something go a little quicker. So the square root of 1 to the 1 power is, of course, just 1. And the natural log of 1 is 0. What exponent do we put on e to produce 1? So it looks like we have a 1/2 times a 1 times a 1. So a 1/2. All right. A particle moves along a straight line with a position function of s. Find the value of t at which the particle reverses its direction. So it can only reverse directions when its velocity is equal to 0. So let's find the derivative of position. So it can only change directions at a critical number, and that would be when the velocity is equal to 0. So this would be at time 3/2. And you can double check, look at your velocity function, check it out here. If you had a value less than 3/2, like t equals 1, can you see that velocity on this value, or this interval rather? V of t would be a negative number, and after that, from 3/2 to infinity, pick a number bigger than 3/2 and you can see that v of t would be positive. So first it was moving left, and then it was moving to the right. So you didn't have to show all of that work. So we know it's changing directions at its only critical number of 3/2. All right, another particle with a position function. Find the value at which the acceleration is equal to 0. Well, s prime is velocity, 3t squared minus 2t. S double prime is acceleration, 6t minus 2. So acceleration is equal to 0 when t is 2/6, or 1/3. All right, 13. Linearization is the same as finding a tangent line. Find the tangent line approximation. So that would mean the same thing here, of using a linear approximation. So we can use the square root function. So our point nearby, our point of tangency nearby, is going to be 16. We know its square root is 4. So we know the square root of 16.2 is going to be a little bit bigger than 4. F prime of x will give us the slope of our tangent. So at specifically at our point of tangency, f prime of 4, we will come up with a slope of 1/4. So our tangent line equation And then we want to substitute to get an approximation when x is 16.2. So we're using our tangent line to approximate the square root curve. So we would have y minus 4 is 1/4 of 0.2. And again, I like fractions. 0.2 would be 1/5. So I might write this as 4 and 1/20th. If you liked decimals better, you would write y minus 4 is equal to 0.25 for the 1/4 and 0.2. You would have to be careful to count your decimal places. So we would come up with, as a decimal, 4.05, which of course is the same as 4 and 1/20th. All right, so I think I have a problem. What did I do? Oh, I guess way back here. What's the point we're trying to plug in here? 16. Ouch. Ouch, ouch, ouch. We're trying to find the slope at x equals 16. I don't know what I was thinking there. So 1 over 2 times 4. So let's try making our slope different here. Let me erase all of this so I don't mess you up a second time. All right. So how about a slope of 1/8? I hope I've got that right this time. And now I want to substitute and let our x equal 16.2. So y minus 4 is 1/8, and then we will still have our 2/10 or 1/5, whichever you prefer. So now I've got 1/40th, so 4 and 1/40th. All right, that looks better. And there's our answer, C. All right, what are we doing here? All right, so here we're using our change in x. So the change in x is equivalent to our dx. So we want to find just the dy. So to get there, don't worry about this problem. We want to find dy dx, same as we usually do, and then we'll do a little bit of work with it. So differentiating this equation, dy dx is equal to 2x. So our differential for dy simply is when we split these up here. So in this problem, it is telling us that we're going to use this delta x as 1. And we want our x value to be equal to 2. So there's simply two givens here. So we're just getting used to that term differential. So our x value is given to be 2, and our dx or delta x is given to be 1. So our dy, so it's like finding the rise when you're given a run. So that would be our value of 4. Linear approximation, and this is at the point of tangency. We're going to, same as letting x equal 0, it's just telling you that it's a specific constant. All right, so our function, and we want to do this at 0. So f of 0 is going to be our point of tangency. So that would be e to the negative 3 times 0. And e to the 0, of course, would be 1. So that's our point of tangency for our linear approximation at 0, 1. And our derivative, f prime of x, the derivative of e to a glob is e to a glob. And then with the chain rule on the glob, so we could bring that out in front. And then we want our specific slope to be when x is equal to 0. So negative 3e to the negative 3 times 0 is 0. So that would be negative 3 times 1, or negative 3. So our slope of our tangent line is our f prime of 0, or negative 3. So here's our tangent. That's the line we're going to use for our approximation. And now we want to, oops, that's all we need to do in this one. We don't need to plug in a specific value. We just need to solve this. So negative 3x plus 1. and turn it around here. That looks like C, negative 3x positive 1. And a second derivative by implicit differentiation. You are getting plenty of practice here. All right, 3x squared. We do not need a chain rule on the x. 3y squared. We do need a chain rule on the y. Equals 0. dy dx, seen it before, negative 3x squared divided by 3y squared. So there's our first derivative. And now let's go right on to our second derivative, quotient rule of that value. So we'll keep the negative out in front. Low d high minus high d low, and that's where we need our chain rule, dy dx, all over low squared. So in multiple choice questions, can you save some time and just do that substitution right away? Yes, do as much as you can in one step, as long as you can avoid making errors. So that dy dx gets replaced with our negative x squared over y squared. And then we go back to our y to the fourth. So our cancellation, this y cancels with one of those y's. And then we wanted to remove the complexity, so we still have a y in the denominator here. So we want to multiply by y times y. And I often forget to distribute, so let's be extra careful about that. So we'll continue up here. So we now have 2xy cubed minus, plus negative times negative. And our y's have canceled out, and we've got 2x to the fourth. All over y is now to the fifth. And if we factor from the numerator an x, then we'll have a y cubed plus an x cubed over a y to the fifth, and we're pretty happy with that because we were expecting to do a second substitution where that becomes a 1. So I hope we have practiced this enough for everyone to have found these getting quite a bit easier. All right, and a whopper of an assignment here. We've seen this before, particle moving along a straight line, where t is measured in seconds, s in meters. So find the distance traveled over 0, 3. All right, so this assignment clearly, I was expecting the repetition here. You may or may not appreciate repetition. It might help you. Some of you might have just sped through this since you've seen it before. So when is velocity equal to 0? Those are the critical numbers, and it is the only time that the particle can change directions. So here is our, and I better not talk here while I'm doing this. 6 goes into 12 2 times. The only time that a particle can change direction is when its velocity hits 0. But just because it hits 0 isn't enough. It might just be a saddle point. It has to cross the axis, so it can't bounce, can't be a double root. Okay, so the only 2 times that this thing could change directions, and they are both single roots, so we are expecting it to change directions at these 2 times. And we could test that out. So on our first interval from, that should both be positives, positive 1 and 2. On our first interval from 0 to 1, if we put 1.5 in here, we found out that we had 6 times a negative number times a positive number. So we knew that the velocity started out to be negative, and it was moving to the left. And then on the interval from 2 to 3, when you pick a number bigger than 2, all of those parentheses are positive, so then it is moving to the right. So now we just have to track where it is at its endpoints and at its critical numbers. So we found its position at time 0, at time 1, and at time 3. Oops, 2, critical number, skipping 1. Also at 2, and then at 3. So we want to take our position function and find those values. And I have 0 meters, 5 meters, 4 meters, and 9 meters. So it traveled 5 meters and then 1 meter backwards and then 5 meters forward. So our total distance was 11 meters. Sorry for the long video again. Hopefully all of these review problems are helpful. Watch only the parts of the videos that you need to, guys.